Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at how we can use valence bond theory to explain how atoms can form double and triple bonds. So a good place to start is looking at our hybrid orbitals. So if I have an atom with, say, 3 electronic domains, my electrons are going to be pulled in 3 different directions, meaning that I need 3 orbitals to do it. So we mix our s and p orbitals to make, say, an sp2 hybridized system. So this means that not all of my p orbitals are going to be mixed into the new set of orbitals. So what happens to these remaining sets of orbitals? Now, if I'm boron, this is actually pretty easy. I don't have enough electrons to fill that vacant p orbital, so it's just left empty. And it's going to have no interaction with the orbitals that actually do have electrons. These orbitals will go on to form bonds. This orbital will just sit there. However, not every atom is only going to have 3 electrons. So if I have something like carbon, what's going to happen with those extra electrons? So if I've got, say, a molecule with double bonds, say something like carbon, I've got 4 electrons. They hybridize to make 3 sp2 orbitals. But this means that I'm going to have 1 orbital left over with an extra electron sitting all alone. Now, my sp2 orbitals are going to go ahead and mix, and I've got 1 electron in each. They'll overlap with a partially occupied orbital on an adjacent atom. So for the hydrogen atoms, this is going to make a sigma bond, which is a way of talking about a direct head-on overlap in between 2 orbitals. In this case, an sp2 orbital and an s orbital. These sigma bonds are actually very attractive, as they have these huge overlap regions. It's one of the reasons why carbon-hydrogen bonds are so stable, and carbon-carbon single bonds do the same thing. Here we've got 2 sp2 orbitals overlapping. These are actually going to be fairly favorable and very stable. However, when I'm looking at these 2 carbon atoms, they have a slight problem. They both have these unhybridized p orbitals, and each one of these p orbitals has an unhybridized electron stuck on. Now I've got 2 electrons sitting in neighboring orbitals that are close enough that we might actually be able to do something with them. So a good way to think about this is what ends up happening is most of the bonding overlap is going to happen this direct head-on collision. However, these 2 orbitals are close enough they can mix together. And this mixing of p orbitals is called a pi bond. So p orbitals make a pi bond. And they don't have a really big overlap region because you'll notice they aren't that close, but they do have an advantage. They can reach over the sigma bond and under it at the same time. So I've got 2 overlapping regions. Neither one's that good, but there is enough overlap here that it will help pull these 2 atoms together. And as a result, what we form is this pi bond, which is going to be much weaker than our sigma bond, but our double bond as a whole is much stronger than a single bond. So pi bonds are weaker than sigma bonds, but a double bond is essentially a sigma bond plus a little. So for those of you who like to do a little construction or something, a good way to think about this is I can go ahead and put a nail to hold two boards together, and that will work pretty well. However, if you really want to make sure that those boards stay stuck together, what you'll do is you'll add a little bit of wood glue. Anybody who's tried to hold 2 boards together with just wood glue knows that doesn't work so well. But when we combine the 2 different methods, this gives us a huge net effect that is way more powerful than just having either one individually. So wood glue is not as good as a nail, but the 2 of them together is really good. Now, if this works for a double bond, we can use the same general idea for a triple bond. The only difference here is that when I have a triple bond, usually what I have here is I've got an sp hybridized atom. Because if I've got a triple bond, this usually means I can only have 2 electronic domains, so I don't exceed the octet rule. And when I've got this sp hybridized atom, this means I've got two unhybridized p orbitals. And these two unhybridized p orbitals can usually overlap with two unhybridized p orbitals on an adjacent atom to form two different pi bonds. So these two pi bonds will be at a 90-degree angle from each other. Both of these pi bonds are going to be weaker than the original direct overlap sigma bond, but they add a whole bunch of extra oomph to my total bond. So a triple bond is better than a double bond, is better than a single bond, more or less because I slap more wood glue on the system to hold it all together. And so when we're looking at bonding character, this is going to be one of the reasons why occasionally you can do such things as make a triple bond fall apart to a double bond, because it's a little easier to cleave a pi bond than it is a sigma. And this is going to be a really important idea as we kind of go forward, because one of the important things about valence bond theory is it is actually a fairly powerful explanatory method, but it doesn't always predict exactly what happens. So for that, we're going to need to bring in more orbital theory next time when we go to full molecular orbital theory. And this is going to use a whole bunch more sigma and pi bonds. So get ready for that next time. Until then, take care.